Hello everyone, my name is Hassan Mansour and I'm with Mitsubishi Electric Research Labs. Today I will talk about our work titled Indoor Airflow Imaging Using Physics-Informed Schlieren Tomography. This is joint work with our intern Arjun from Carnegie Mellon University, along with my colleagues Wael and Joshua Rapp from MERL. Our goal is to develop an airflow sensing system that uses only a camera and potentially an LED projector to reconstruct the 3D distribution of air inside of a room. The idea is based on Schlieren imaging, and specifically background-oriented Schlieren imaging, where you place a camera on one side of the flow, and that is focused on a textured pattern on the opposite side of the flow. And that textured pattern could be produced by a projector, for example. And from the observed images by the camera, we want to be able to reconstruct the 3D airflow volume as a result of variations in the refractive field that the airflow is causing. We chose BOSS imaging over other techniques because it is less expensive and provides more flexibility in terms of the imaging environment. And the way it works is that as air flows through the room and as a result of the change of the temperature of the air, that causes a change in the refractive index gradient. And so, as a result, the image that's captured by the camera exhibits slight distortions compared to an image that is captured when there is no flow in the room. And the distortions are due to the slight deflections of the rays of light as they refract through the volume. This has had several applications in physics, and there's also been some other toy examples for a similar type of BOSS setup where the convection flow above an espresso cup has been reconstructed using multiple cameras. In our setup, the challenge is that we want to perform quantitative 3D airflow sensing from just one single camera view, and in the presence of non-localized turbulent flows. And so our formulation or our perspective is to set this up as an inverse problem where we observe the Schlieren effect as the measurements D, and we want to reconstruct the airflow parameters, which we represent by M, and the observations are captured through a forward model F that maps from the parameter space to the observable space. And all this is in the presence of noise. Now, to give you a pictorial view of what the Schlieren effect looks like, let's suppose that you have a projector and camera located on one side of the room, and the projector is projecting a pattern onto the back wall. The camera observes that pattern undisturbed when there's no flow. However, when there is a flow that's causing a change in the refractive field, then the camera observes a similar picture, but in this case it would be slightly different than the reference picture when there's no flow. And to visualize that difference, actually, if we compute the intensity difference between the two images, we can now actually see the Schlieren effect, where you can see that there's a distortion in the texture, specifically in the locations where the flow exhibits the highest density gradient. And as a result, the refractive index gradient. And so our task is to map from the observables, which is the Schlieren image, back to the parameter space, which we'll refer to as M in this case. So this is a classical ODE or PDE constrained optimization problem where we want to solve for the parameters M by minimizing the data misfit J, plus some regularization function or penalty function that imposes structure on the object, and while satisfying some of the physics constraints which are represented by U equals F of M. So our problem can be set up as a classical ODE or PDE constrained optimization problem where we want to reconstruct the parameters M of the flow by minimizing the data misfit term, which is represented by J in this case, plus some regularization function, subject to the constraint that the flow has to obey the physics of the problem. And so given the rendered Schlieren image I, we want to map back, or we want to relate that image I to the refractive index of the airflow itself. And the way that we would do this, or that we can do this, is using the refractive radiative transfer equation, which specifically says that the propagation of a ray of light is governed by the ODE, which is what we see on the left-hand side, which is dx by dt is the velocity field, or the orientation of the ray of light, and the variation of the velocity field, or the direction of the ray of light, is given by eta multiplied by the gradient of eta at a specific location in space. And so ultimately, the resulting image that we see at the camera corresponds to a path integral over the direction of the ray of light going from the back wall all the way to the camera. And so the motivation for using this approach, where we combine nonlinear ray tracing with the path integral expression for the RRTE, is that existing tools or existing formulations, they discretize the refraction of the rays of light, and they result in biased rendering. And so our contribution in this context is the use of this nonlinear ray tracing formulation and the evaluation of the path integral using an efficient, unbiased Monte Carlo estimators. We also implemented the light propagation using JAX library that allows for parallelization and integration in machine learning libraries. And we also have an efficient gradient computation through the ray tracing procedure that relies on the adjoint method. And this constitutes, to our knowledge, the first differentiable physically based renderer for background-oriented Schlieren. Now, in terms of optimization algorithms and how would we solve such a problem? Well, generally, as we said, we want to minimize for the parameters M that minimize the measurement mismatch, which is defined by J, subject to the forward model, which is governing the ray propagation, or specifically in this case, the image formation as a function of the parameters M. But in addition to that, we have additional constraints, which are specifically used to regularize the reconstruction. And here we are using P to represent the differential equations that govern the flow M, as well as boundary conditions represented by B that need to be imposed on the boundary of the volume. And one way to incorporate this sort of regularization is to use a physics-informed neural network type of parameterization, where now the flow parameters that we are interested in, so M, can be parameterized itself using the weights of neural networks. And now the whole problem can be recast as a neural network weight estimation problem, where the weights theta now need to be computed in order to minimize the measurement mismatch loss J, plus the airflow PDE loss P, or L of P in this case, plus the boundary loss LB. And here you can see that we lifted the hard constraints on P and B into the objective, and resulting in a multi-objective or multi-loss problem. So what does that look like for specifically the airflow problem? As we said, the main challenge is that we have a single view 3D boss, which is severely ill-posed. And the airflow parameters that we're interested in are the temperature, pressure, and velocity distribution. And so we approximate the physics of the airflow using a Boussinesq approximation of Navier Stokes equations, and that constitutes our PDE loss. And the way that this PDE loss relates to the refractive index, the airflow parameters relate to the refractive field, is through the eta, basically the Gladstone-Dale equation, which is shown over here as eta equals 1 plus rho g T0 over T. And finally, the airflow parameters themselves, so TP and U, are parameterized using a multilayer perceptron that has weights theta. And so now we're solving for the weights theta that generate the temperature, pressure, and velocity profiles. A pictorial view of our formulation looks like this. We actually have two types of coordinate representations for the flows. The first type is on a 64 by 64 by 64 grid, and that is primarily used to efficiently run the differentiable renderer to map intensities from, or luminance, let's say, from the back wall to intensities on the image. And then we also have collocation points that are defined anywhere within the space, and those are used to penalize the PDE loss. And finally, we impose the boundary loss on all sets of sampled points, whether they're the grid points or the collocation points, through the boundary loss. And our MLP actually uses random Fourier features, which helps to mitigate spectral bias and non-dimensionalization, as well as our use of gradient-based adaptive loss balancing that allows us to achieve faster convergence and better performance overall. Now, in terms of the simulation setup that we built, we used OpenFOAM with RAND steady-state simulation using the buoyant Boussinesq simple foam solver. We simulated a room of size 5.1 by 4.6 by 3 meters, and the simulation uses the K epsilon turbulence model, and we're specifically here interested in the heating case. The bus measurements are captured using a camera only, and then we also use a camera and projector combination, and the back wall is illuminated with a wavelet noise pattern. The airflow reconstruction assumes that we have full knowledge of the boundary wall. Basically, it's the wall where the inlet outlet is located. And we render actually the reconstruction on a 64 cubed grid. So overall, we have actually a resolution mismatch in this problem, as well as a physics mismatch, since the actual OpenFOAM simulation runs RANDs, whereas the reconstruction actually uses an approximation of Navier Stokes equations. So on the left-hand side over here, you see the ground truth flow, as well as the locations of the camera and the projector, and the corresponding camera Schlieren image. And in the three columns that you see on the right-hand side over here, we show the reconstructions corresponding to minimizing only the BOS plus boundary loss in the left-hand side column. Reconstruction with only the PDE constraint or PDE loss, as well as the boundary loss in the middle column, and then the reconstruction using our proposed formulation, which combines the BOS, PDE, and boundary losses. And on the bottom row, you can see the error plots in the field. And so visually, you can see that the right-hand side reconstruction actually is more faithful to the true airflow temperature distribution. And numerically, we can also see that that is truly the case. Actually, when we combined all three losses, the error in reconstructing the temperature, pressure, and velocity is minimized when both BOS, PDE, and the boundary loss are combined together. And so, to conclude, we have proposed a physics-informed BOS imaging setup, which leverages physics-based regularization using the PINN, as well as differentiable renderer to perform nonlinear ray tracing. And this was all done for a single view BOS imaging. And for the extensions that we foresee, we expect that we will want to update or upgrade basically the physics constraint so that we are able to impose a RANS-based PDE model in the reconstruction. And we would like to explore better multi-objective loss balancing. And finally, we would like to perform sensitivity and uncertainty quantification analysis. Thank you for listening, and have a good day.